For question 15 from the homework, we're given the information about a power output of a laser is measured by its wattage, the number of joules of energy it radiates per second, right? Wattage is the number of joules of energy it radiates per second. So 20-watt laser, right, would be 20 joules per second. So a 20-watt laser produces a beam of green light with a wavelength of 520 nanometers. Calculate the energy of the photons and the number of photons emitted. There's a couple ways that we can do this because we know that watts, right, equals joules per second. And we know this is a 20-watt laser, so we know that that's 20 joules per second, right? Calculate the energy of the photons and the number of the photons. So calculate the energy by each photon. A few other ways we can calculate it is also, we know the wavelength of light, and we know that, right, energy equals Planck's constant times my frequency. I could take that light, I could use that to find the frequency, find the energy. We also know an equation that combines those where energy equals Planck's constant times speed of light divided by my wavelength to find the energy that way. So let's start with what we know, right? We're looking for energy. Energy equals Planck's constant, 6.626 times 10 to the minus 34 joules times second. Right, our speed of light, 2.998 times 10 to the 8th meters per second, all over our wavelength. Our wavelength, 520 nanometers. I guess we should have started with converting that into meters, right? We know 1 times 10 to the 9 nanometers is 1 meter. So our wavelength is 5.20 times 10 to the minus 7 meters. So write that in here, 5.200 times 10 to the minus 7 meters. Multiply and divide, and we should get the energy equals. And just to check our units real quick, right? Units of energy, energy should be in joules. So if we take a look, right, when I multiply, seconds cancel out. When I divide, my meters will cancel out, and I'm left with joules. So our energy should be approximately 3.820 times 10 to the minus 19 joules. That's the energy of one photon, right? One photon carries that much energy. We need this information to answer the next question, part B. So there are two ways that we can solve this equation. The first way is giving the information, right, that we were told. This is a 20-watt laser, and we know that 1 watt equals 1 joule per second. So, okay, that 20-watt laser, we have 20 joules per second. So we want to know, right, if I have 20 joules per second, and I run that laser for 1 second, right? I have 1 second of time. Seconds cancel out, so I have 20 joules. I want to find out, right, the number of photons. Well, if I have 20 joules of energy, and I know from the previous question, we found that 1 photon of light equals 3.820 times 10 to the minus 19 joules, right, per 1 photon of light per photon. So, okay, 20 joules total. If each photon of energy is bringing this much energy, how many total photons would I need? That's like saying, okay, I need $20 and I have quarters. So how many quarters do I need, right? I've got 25 cents. Each quarter brings 25 cents. I would divide that in to see how many would go into this total. I need 20 joules of energy. Each photon brings this much energy. So we can divide 20 joules by 3.8 times 10 to the minus 19 joules per photon, right? We're going to end up with photons of energy. We're going to end up with approximately 5.236 times 10 to the 19 photons, right? A lot of photons would be required to make 20 joules of energy. That's one way to solve this problem. Another way to solve the problem, another way that would work to answer this, be using the equation energy equals N, right? Our energy level N times Planck's constant times our frequency, where we know, right, 520 nanometer light, we'd convert that to meters. We could find the frequency of that light based on the wavelength, right? The frequency is going to be something like 5.765 times 10 to the 14th. We know Planck's constant, and we know the total energy we're looking for. We're looking for 20 joules, right? Okay, N in this case would give us how many photons would we need to obtain 20 joules of energy, given Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, right, in 1 second, right, and our frequency of 5.1765 times 10 to the 14. In this case, right, frequency is inverse seconds. This would still give you the right number, right? It would still give you the same number that we got here, the number of photons. So both of these would give you the correct answer. They're both a little bit different pathways. So don't be worried, right? That if you use the second pathway here and Chem 101 only offered this pathway as the correct answer, you are not incorrect using this pathway. It's a little, it's not exactly what this equation was designed for, but it will still yield the same result, whereas we're interpreting N to be the number of photons of light based on this frequency and the total energy that we need, right? That'll yield the same result. We'll still get 5.236 times 10 to the 19 photons of light.